Hello viewers, I am B. Asghar Pasha, Assistant Professor, Department of Mathematics, MSRIT. Now I am going to talk about linear differential equations with variable coefficients, which is a part of Module 2, Differential Equation 2 of Engineering Mathematics 2. The prerequisite for this is the knowledge of linear differential equations with constant coefficients. As you know, if I have a linear differential equation of this type, 4d square plus 3d plus 2y equals to some function of x, maybe e to the power of 2x plus cos x, whatever it may be, where as you know d indicates derivative with respect to independent variable x. Solution of this, of course I am talking about this constant coefficients. Solution of this equation consists of two parts. What we do is, we first find general solution of homogeneous part of this differential equation. What is homogeneous part? 4d square plus 3d plus 3d plus 2 of y, this is a differential equation, equals to 0. This is a homogeneous part. We find solution, general solution of this homogeneous part of the differential equation, which consists of two arbitrary constants, two of course due to the order of the differential equation. Okay, so I'll get some solution u, which is a general solution consisting of two arbitrary constants. Next, I will solve the entire equation, entire given equation, which is a particular solution v, which does not involve any arbitrary constants, means it satisfies the differential equation containing no arbitrary constants. This is a homogeneous part, v is a solution of entire differential equation. Now u plus v together, u plus v will be a solution of this entire differential equation. U is known as a CF and v is known as particular integral. You are familiar with this. Y equals to u plus v is a solution. Now, this rule is applicable when equations, when coefficients are constants. And we have some general rules for finding a complementary function. As you know, depending on the nature of the roots, depending on the nature of roots of auxiliary equation, if the given linear differential equation with constant coefficients is written in the form f of d of y equals to phi of x, then what is auxiliary equation? F of d equals to 0, or fine, I can take it as m, f of m equals to 0. Roots, okay, roots, you have to find roots of this auxiliary equation. Depending on the roots, we write complementary function. For example, if roots are real like this, real and distinct 1, 2, 3, CF is C1 into e to the power of x, where x stands for independent variable, plus for another constant, for another root 2, we write one constant C2 into e to the power of 2x, plus for 3, another constant 3 e to the power of 3x. What is this? This is a complementary function corresponding to roots of auxiliary equation. Now, suppose roots are repeated. For example, 2, 2, 2. Roots are repeated. For repeated roots, complementary function is like this: C1 plus C2 into e to the power of 2x, not okay, C2 into x. X is a independent variable, C2 into x plus C3 into x square. 3 roots. If there are 4 roots, then one more, C4 into x cube into e to the power of 2x. So, you are familiar with this notation as well. Suppose roots are complex, alpha plus or minus I beta, complex roots. Then complementary function is e to the power of alpha x into, alpha is the real part, into C1 cos beta x plus C2 sin beta x. Okay. Same thing, similar rule can be applied if complex roots are repeated. This is with respect to complementary function. I will quickly talk about particular integrals. F of d of y equals to phi of x is the given differential equation. I am talking about linear differential equations with constant coefficients. Now, particular solution means the value of y which satisfies this differential equation, which is y equals to 1 over f of d operated on phi of x. Right. We have some shortcut techniques when phi of x takes standard forms. As you know, when phi of x is e to the power of ax, the rule is we have to just replace d by a in the denominator, provided denominator is not equal to 0. If denominator becomes 0, then the rule is x into 1 by f dash. You just differentiate the denominator and then operate it on phi of x. The same rule follows. Now you replace d by a provided f dash of a, that is denominator is not equal to 0. If denominator becomes 0 again, then y will be x square into 1 by f double dash of d operated on phi of x, and so on. You continue the procedure. Now suppose phi of x is sin of ax plus b or cos of ax plus b. The rule is y is 1 by f of d is an operator operating on sin of ax plus b. We have to replace d square by minus of a square. Same rule, if denominator doesn't become 0 with the substitution. If denominator becomes 0, then you multiply this with an independent variable, differentiate the denominator and then proceed with the same procedure of replacing d square by minus a square. Of course, this is applicable when you have even powers. If you have odd powers, if you are left with odd powers at the end, you just divide and multiply by conjugate of it and replace d square by minus a square after that stage. This is with respect to sin of ax plus b. Same rule is applicable for cos of ax plus b also. So, I will be using it. Next, the third rule for polynomial functions when phi of x is a polynomial. Y that is equals to 1 by f of d operating on phi of x. As you know, you have to write f of d as 1 plus some function, let it be some g of d 1 plus x, and then take it to numerator. So, y becomes 1 plus g of d the whole inverse operating on phi of x. Now, you expand this by binomial theorem. You know 1 plus x whole to the power of minus 1 is 1 minus x plus x square minus x cube plus x to the power of 4 plus dot dot dot. 1 minus x whole to the power of minus 1 is 1 plus x, all positive terms here, 1 plus x square plus x cube plus x to the power of 4 and so on. Of course, in general, instead of 1, if you have any other power, So use this result. 1 plus x whole to the power of n is 1 plus nx plus n into n minus 1 by 2 factorial into x square plus dot dot dot. Next is n into n minus 1 into n minus 2 divided by 3 factorial and so on. So use this technique, and then you will get an infinite series in terms of d. As phi of x is a polynomial, certain order derivatives of phi of x will be 0 after some stage, it will be 0. So you can easily find particular integral. Fine. There is a shortcut method, you know, a division method of solving this. I'll talk about it when I solve problems based on variable coefficients. Type 4 is of course of this form when phi of x is e to the power of a of ax into some v. V can be cos ax or polynomial, whatever it may be, some function of x. Now pi equals to 1 over the operator containing constant coefficients e to the power of ax into v. Now rule is, you take out e to the power of ax, take e to the power of ax outside the operator after replacing d by d plus a. So it is like this, e to the power of ax 1 by, you just replace d by d plus a and operate it on v. So denominator is some operator, again it is like a polynomial in d. If v is a known function, you operate it, like it may be type 1 e to the power of x, it may be type 2 cos ax, it may be type 3 polynomial. Fine, so you can do that. If it is some general functions, yes, complicated, we have to use the general procedure of evaluating any function 1 plus d plus a phi of x. We have to use the general procedure, a complicated one. When we treat this as phi and cross multiply, we get a Leibniz linear equation, and the solution of that gives the particular integral. Fine. And there is one more technique when x is multiplied with v. X is multiplied with v. For that, you can use real and imaginary parts of e to the power of ix concept. You can take you can reduce that type to type 4 and solve. So these are all essential things required for today's talk. Yes, now I'll go back to the actual slide. Today's topic is linear differential equations with variable coefficients. What I meant was, yes, this one, x to the power of n, nth derivative. These are variable coefficients. I cannot apply the rules which you have studied, okay, which are related to constant coefficients. That is applicable, of course, when the equations are linear. You know the meaning of linear. Linearity in the sense degree should be 1, degree of the derivative as well as dependent variable 1, and derivatives, product of derivatives or product of dependent variable and derivatives should not be there. So and so conditions. Linearity, you know what linear means. It's a linear equation for sure, because powers are all 1, meaning degree is 1, degree of all derivatives of 1 plus the coefficient is not y, that is not product of dependent and derivatives is not there, correct. So it is a linear differential equation for sure, no doubt about it, but the main problem is coefficients are not constants, they are variables, x to the power of n minus 1, but not all differential equations with variable coefficients can be solved easily. Okay, to solve such equations, first of all we have to think of substitutions which reduces these equations to constant coefficients, linear differential equation with constant coefficients, or else we may have to go with numerical techniques to solve such equations. Now there are two special categories which can be easily solved using standard substitutions. The first one is Cauchy's differential equation. It's a special type. You can see the coefficient of nth derivative dny by dx power of n is x to the power of n preceded with some constant an. It's a constant. Coefficient of n minus 1th derivative is x power of n minus 1. Coefficient of n minus 2 derivative is x to the power of n minus 2. So it follows some pattern. Such differential equations are known as Cauchy's linear differential equation. Special type, of course, here coefficient of y is constant, a naught. All these are constants, a naught, a1, a2 till a naught. And phi of x can be any function. It can be a function of x or constant. Now, how to reduce this to a differential equation into constant coefficients? You can reduce it to a differential equation with constant coefficients using the substitution x equals to e to the power of t. If x is e to the power of t, means I am changing the independent variable. If x is e to the power of t, then t becomes log x. So that x becomes a composite function now. It's like y is a function of x is a function of t. So actual derivative dy by dx becomes dy by dt into dt by dx, chain rule, dy by dt into dt by dx. What is dt by dx? T is log x, so dt by dx is 1 by x. Now cross multiply, you will get x into dy by dx equals to dy by dt. So what has happened here? In our differential equation, we have x into dy by dx term, that is coefficient of dy by dx is what? Is variable. Now what we have? We have dy. The coefficient d is of course a derivative with respect to new variable t. The coefficient of dy is 1, constant coefficient. So we have converted variable coefficient term to a constant coefficient term. This is with respect to first order derivative. What happens to second order derivative? D square y by dx square. Okay. I will write this as d by dx of dy by dx, and then I will use the substitution. I will use the value of dy by dx which I have got in the previous slide. Dy by dx is dy by dt into 1 by x. Now I use product rule, d by dx of dy by dt into 1 by x. First function as it is, differentiation of 1 by x, which is minus 1 by x square, plus second function as it is, differentiation of first function. Okay, I will write this term as it is, dy by dt into minus 1 by x square plus 1 by x into dy by, okay, here dy by dt, it is like z, which is a function of t, and t is internally function of x, t equals to log x. So same chain rule you have to apply. It is d by dx of dy by dt, which is equivalent to d by dt of dy by dt into dt by dx, chain rule. First differentiate z with respect to t and then t with respect to x. So that derivative 1 by x, now I will differentiate this term, which is d square y by dt square, and dt by dx is 1 by x because t equals to log x. Now I will write this d square y by dx square as d square y. So I am denoting d as d by dt. With this, you can see I have written d here. D square y, I will cross, okay, I will take 1 by x square common, it becomes d square y minus dy into 1 by x square, cross multiply x square, so it is x square into d square y by dx square equals to d square y minus dy. So finally x square into d square y by dx square equals to d into d minus 1 into y. What is it? This is a term with variable coefficients. Now you have the corresponding transformed term whose coefficient is 1, which is a constant. Similarly, third order term x cube into d cube y by dx cube can be written as d into d minus 1 into d minus 2 into y, and so on. So, using this substitution, you can convert the given differential equation, which is of variable coefficient, to equation involving constant coefficients. Okay, substituting this in the given differential equation, as I said earlier, we obtain linear differential equation with constant coefficients, which can be solved easily, of course, which can be solved easily by known techniques. Let us take an example. X square into y double dash plus x into y dash plus y equals to 2 cos square into log x. You can see here, this is x square, coefficient of y double dash is x square, coefficient of y dash is x, coefficient of y is constant, that is important, equals to 2 cos square log x. So, it satisfies all conditions of Cauchy's theorem, or what is that, Cauchy's differential equation. Yes, it is in the standard form. It is Cauchy's differential equation. I will reduce it to equation with constant coefficients using the substitution x equals to e to the power of t. So, that t is log x, x dy by dx is dy, x square d square y by dx square is d into d minus 1 into y, where as usual d is d by dt. If I substitute all these things in the given equation, I obtain this d into d minus 1 into y plus dy plus y equals to 2 cos square t. I do not have a formula, shortcut formula for cos square t, because I have taught you, I told you, yes, if it is e to the power of ax, replace d by a. If it is cos ax plus b or sin ax plus b, replace d square by minus a square, provided denominator is not equal to 0. So, rule is applicable for such standard functions. So, you have cos square t here, convert it to linear form. You know that 2 cos square t is 1 plus cos 2t. If it is 2 sin square t, we would have written it as 1 minus cos 2t. So, 2 cos square t is 1 plus cos 2t. I have converted it. Next, I will simplify this. I will get d square plus 1 of y equals to 1 plus cos 2t. Yes, this is a reduced equation. It is an equation with constant coefficients. You know how to find its solution now. So, I will quickly go about its solution. D square plus 1 of y equal to 1 plus cos 2t is my equation. So, auxiliary equation is obtained by replacing d by m in the homogeneous part of the differential equation. So, it is m square plus 1 equals to 0. You solve that equation, you get roots as 0 plus r minus I. So, roots are complex. Real part is 0, imaginary part is 1. Therefore, CF is C1 cos t plus C2 sin t, e to the power of 0 t into C1 cos t plus C2 sin t. This is about CF. Now, particular integral, it is 1 by d square plus 1 into 1 plus cos 2t. I will write 1 as e to the power of 0 t plus cos 2t as it is. I will operate 1 by d square plus 1 on both 1 and cos 2t. So, 1 by d square plus 1 e to the power of 0 t plus 1 by d square plus 1 cos 2t. Yes, I will call this as Pi1 and this part as Pi2. I will consider Pi1, which is 1 by d square plus 1 into e to the power of 0 t. According to rule 1, you have to replace d by 0, provided denominator is not equal to 0. So, I have replaced it by 0, 0 plus 1 into e to the power of 0 t. So, answer is 1, Pi1 is 1, Pi2. Pi2 is 1 by d square plus 1 cos 2t. You have to replace d square by minus a square. What is a here? A is the coefficient of t, a is 2. So, you have to replace d square by minus of a square, which is equals to minus 4. Next, with this substitution, Pi2 becomes 1 by minus 4 plus 1 into cos 2t, that is minus 1 by 3 into cos of 2 log x. What I have done? I have replaced t by log x, because according to my substitution, x is e to the power of t and t is log x. Now pi equals to, so I will club both pi1 and pi2 now. Pi1 is 1, pi2 is minus 1 by 3 cos of 2 log x. This is pi. The complete solution of the given differential equation is y equals to cf plus pi. So I have written it. So this is a solution of Cauchy's differential equation, a particular one. Now problem to another Cauchy's differential equation. X square y double dash minus 5x y dash plus 8y equals to 2 log x. Yes, it satisfies all those conditions, of being what? Of a Cauchy's differential equation. Same step, same procedure. Take x as e to the power of t. Then x into dy by dx becomes dy. X square y double dash becomes d into d minus y. When you substitute all these in the given equation, you will get d square minus 6d plus 8 of y equals to 2t. So auxiliary equation is m square minus 6m plus 8 equals to 0. Done. Now I will factorize it. M square minus 4m minus 2m plus 8 equals to 0. You find the roots. Roots are 2 and 4. Roots are real and distinct. And complementary function is c1 into e to the power of 2t plus c2 into e to the power of 4t. I have used law of indices here. As you know, we can write e to the power of mn as a to the power of m whole to the power of n. So I have used that here. E to the power of 2t is written as e to the power of t the whole square. Similarly, e to the power of 4t is written as e to the power of t whole to the power of 4. E to the power of t according to our assumption is x. So it is c1 x square plus c2 x to the power of 4. Next, pi. Pi is 1 by d square minus 6d plus 8 operating on 2t, which is a polynomial. So type 3. I have taken 1 by 8 common. Then it is 1 plus d square minus 6d. You can see here 1 plus d square minus 6d divided by 8 operating on 2t, and then I took this to numerator, so it becomes 1 plus d square minus 6d by 8 whole to the power of minus 1. This is like 1 plus x whole to the power of minus 1, and 1 plus x whole to the power of minus 1 expansion is 1 minus x plus x square minus x cube and so on. You can see the same thing here, 1 by 4 d square minus 6d by 8, which is like x, 1 minus x plus x square, d square minus 6d by 8 the whole square plus dot 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 operated on t. So we get 1 by 4 into 1 plus 3d by 4 into t. Why this? Listen, d square minus 6d by 8 plus d square minus 6d by 8 the whole square and so on. So it's an infinite series. When you operate d square on t, it becomes 0, second order derivative of t is 0. So I have ignored that term. Yes, when you operate this on t, it exists. So I have included that, I have retained that term, which is 3d by 4. Next, when you expand this, powers of d in all terms are more than or equal to 2. So second order derivative of t are 0. Same thing followed, for other terms in the infinite series. So I have ignored all the terms excluding 1, which is 3d by 4. 1 plus 3d by 4 operated on t. So it is equals to 1 by 4. Now you multiply 1 into t is t plus 3d by 4 operated on t. This term as it is, 3 by 4 as it is, d of t, d stands for differentiation, differentiation of t is 1, so it is 3 by 4. So finally pi is t by 4 plus 3 by 16. Yes. You should be careful while using binomial expansion. You can see the previous slide. I have taken 8 common. 8 times 1 plus d square minus 6d by 8. What happens if I take d square common? Because ultimately I want 1 as a first term in the 1 plus x. I want 1. that could be achieved by taking d square outside or minus 6d outside or 8 outside. I took 8 out. Instead of that, if I take d square out, what happens? So I'll just explain. D square minus 6d plus 8. Pi is, okay, Pi is 1 by d square minus 6d plus 8, assume some operator operating on 2t. Instead of taking 8 common, if I take d square common, what happens? D square 1 minus 6d minus 8 divided by d square operating on 2t. Okay, this is equals to this is equals to 1 by d square. I'll take this to numerator, which is 1 minus 6d by d is 6 by d minus 8 by d square operating on 2t whole to the power of minus 1. Okay, now it's like 1 minus x whole to the power of minus 1. Right. Now I'll expand it. Pi equals to 1 divided by d square as it is into expansion of this 1 plus, because it's 1 minus whole to the power of minus 1. So all terms are positive. It is 1 plus, yes, I'll write this 6 by d minus 8 by d square plus square 6 by d minus 8 by d square the whole square plus dot 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 operating on 2d. I'll just erase this. Okay, this is an infinite series. I cannot ignore terms here as I did in the slide which I showed you. I cannot ignore terms here. I ignore d square terms there, d cube terms there, because derivatives of that with respect to a polynomial of degree 1 are 0. So I have ignored it. But here, what 1 by d represents here? 1 by d or 6 by d. This 1 by d represents integration. 1 by d square represents integration. Here you have d cube term, d to the power of 4 term. You have terms like this, 1 divided by d to the power of 100. So there are infinite number of terms. All these represents integration. I cannot ignore. 1 by d of t is t square by 2. It increases. 1 by d square of t. Of course, it's a polynomial of degree 3 and so on. I cannot ignore terms here. So if I truncate it, I'll get a truncation error for sure, which is not a solution of the given differential equation. I cannot truncate it. So you should be careful while selecting using terms in the binomial expansion. Okay. So I have taken 8 outside. I have expanded it. You can see there is no d in the denominator, and I can ignore d square and d cube term, and I'll arrive at this value pi equals to t by 4 plus 3 by 16 as I explained earlier. So the complete solution is y equals to cf plus pi. This is one method of evaluating when you have a polynomial t. Answer is t by 4 plus 3 by 16. I'll show you one more method of arriving at this result. What is the polynomial? It is d square minus 6d plus 8 is the operator. D square minus 6d plus 8. I'll write that in increasing order. 8 minus 6d plus d square, increasing order, and phi of t was 2t. 8 minus 6d plus d square, 2t. I'll multiply 8 with 1 by 4 into t to get 2t. I need 2t to be multiplied, normal division technique. So if you multiply by t by 4, 8 times t by 4 is 2t. Then I have operated 8 on t by 4, you have to operate 6d also. D stands for derivative, derivative of t by 4 is 1 by 4, 1 by 4 multiplied with minus 6 is minus 3 by 2. This part minus 6d operated on t by 4, minus 6d operated on t by 4 gives minus 6, derivative of t by 4 is 1 by 4, which is minus 3 by 2. Okay. Now you subtract this, two t vanishes, I will get 3 by 2. Next, what should be multiplied with the 8 to get 3 by 2 here? Definitely it has to be 3 by 16, because when you multiply by 3 by 16 you will get 3 by 8, subtract, you will get 0 as answer. Fine. So this t plus 4 plus 3 by 16 is pi, which we got here, same answer, t by 4 plus 3 by 16 using binomial theorem, binomial expansion. Right, choice is left to you. You can opt for division method, which is usually suitable when you have more terms, and the binomial expansion when you have only 2 terms, like 1 plus d, d square plus d cube. If there are only 2 terms, you will get quick answers, in simple steps using binomial expansion. Otherwise, you prefer division method. I have explained both. Now, let us go to next problem. Complete solution I have written. Of course, I have converted t to log x, which is our assumption. Now, problem number 3. Solve x cube into d cube y by dx cube plus 2x square into dy by dx plus 2y equals to 10 into x plus 1 by x. You can say coefficient of d cube y by dx cube is x cube, coefficient of d square by dx square is x square with some constant 2, coefficient of y is 2. So, it is Cauchy's differential equation. Put x equals to e to the power of t, then t becomes log x as usual. X dy by dx becomes capital D into y, x square d square y by dx square becomes d into d minus 1 into y, x cube d cube y by dx cube becomes d into d minus 1 into d minus 2 into y. When you substitute all this in the given equation, we get this d cube. After simplification, we get d cube minus d square plus 2 of y equals to 10 into e to the power of t plus e to the power of minus t. So, this I have converted, x is e to the power of t, 1 by x is 1 by e to the power of t. Convert x in terms of t, express everything, because LHS is a derivative with respect to independent variable t. Now, auxiliary equation is m cube minus m square plus 2 equals to 0. Now, it is a cubic equation. The easiest way of solving this is guessing one root by inspection and finding remaining roots using synthetic division. By inspection, yes, you try with 0, plus 1, minus 1, plus 2, minus 2, check whether it satisfies or not. Yes, in this case when m is 1, I am getting solution. Yes, I am getting a root, it is satisfying that equation. M equals to minus 1 is a root. Now, I have to find remaining roots using synthetic division. What is that? I will write the coefficients of this. Coefficient of m cube is 1, coefficient of m square is minus 1, coefficient of m is missing, which is 0, then the constant term 2, 1 minus 1, 0, 2. Root is m equals to minus 1 is root. Next, procedure is write 0 here, add 1 plus 0, 1 plus 0 is 1, you multiply these two terms, 1 into minus 1, which is minus 1, add these two, minus 2, multiply, you will get plus 2, add it, 2, 2 into minus 1 is minus 2, 0, you should get 0 here. Okay, so that is x minus 1 is a factor, that is m plus 1 is a factor, and when you divide m cube minus m square plus 2 equal to 0 by m plus 1, you will get remainder as 0. Now the new depressed equation, that is reduced equation, contains these terms as coefficients, that is 1 into x square minus 2 into x and the constant as it is, which I have written here. Okay, x is unknown, of course I have denoted it by m, it is m square 1 into m square minus 2 into m plus 2 equals to 0. Okay, it's a quadratic equation, you can easily solve this. Roots of this equation are 2 plus r minus root of 4 minus 8 divided by 2. So roots are complex, 1 plus r minus I. One root is real, which we have guessed, minus 1, and the other two are complex conjugates, minus 1, 1 plus r minus I. Now complementary function, the first term is a part of CF corresponding to a real root minus 1, it is C1 e to the power of minus t. The other part is part of CF with respect to complex roots, 1 plus r minus I, real part is 1, imaginary part is 1. So e to the power of t into C2 cos t plus C3 sin t. Next, we have to convert this in terms of x. The same law of indices, I have written e to the power of minus t in the second stage as e to the power of t whole to the power of minus 1. This e to the power of t is x, this t is log x, t is log x. E to the power of t is x, x power of minus 1. So CF is C1 by x plus x into so and so. This is a complementary function. Now particular integral. I have taken the operator 1 by d cube minus d square plus d as it is, where d is an operator with respect to independent variable t. This is right hand side, 10 into e to the power of t plus e to the power of minus t. You operate it on both the terms, taking 10 outside. So I will get pi1 and pi2. We have to compute these two. Next, consider pi1. pi1 is 1 by d cube minus d square plus 2 operated on e to the power of t. It is rule 1. We have to replace d by 1. So pi1 will be 1 divided by 2 into e to the power of t. pi2. pi2 is 1 by d cube minus d square plus 2 operated on e to the power of minus t, as you know, minus 1, that is this coefficient. As minus 1 is a root, denominator will become 0 for sure. Denominator is 0. So we have to use this rule. We have to multiply by independent variable, which is t into 1 by 3d square minus 2d, which is derivative of f of d. I have differentiated it. Now replace d by 1, usual procedure. You will get t into e to the power of minus t by 5 as answer. Now substitute in pi, which is 10 times pi1 plus pi2. I have substituted pi1 and pi2 values, and then I have converted that in terms of x. E to the power of t is x, t is log x, and I have used law of indices here. E to the power of minus t is e to the power of t whole to the power of minus 1. You just simplify it. Pi reduces to the form given, which is 10 into x by 2 plus log x by 5x. The complete solution is CF plus pi. We will take up the next example. Problem 4. X cube into d cube y by dx cube plus 3x square into d square y by dx square plus x into dy by dx plus 8y equals to 65 times cos of log x. Yes, coefficients are according to the rule, so it is Cauchy's differential equation. Use a substitution, x equals to e to the power of t, then t becomes log x. As usual, x dy by dx becomes dy, x square d square y by dx square becomes d into d minus y, and so on. Substitute in the given differential equation. We get d cube plus 8 of y equals to 65 cos t. which is a linear differential equation with constant coefficient whose auxiliary equation is m cube plus 8 equals to 0. Next, you can write 8 as 2 cube, m cube plus 2 cube equal to 0. Next step, a cube plus b cube formula, which is m plus 2 into m square minus 2m plus 4 equal to 0. You solve this using usual techniques. You will get roots as minus 2, 1 plus or minus I into root 3. So again one real root which is minus 2 and a pair of complex roots. So the complementary function is c1 into e to the power of minus 2t plus e to the power of 1t, that is real part, into c2 cos root 3t, root 3 is imaginary part, plus c3 into sine of root 3t. Now use law of indices, you write e to the power of minus 2t as e to the power of t whole to the power of minus 2 plus, I have written x which is e to the power of t, write t as log x, convert it everything in terms of x which is cf. Now pi, 1 by d cube plus 865 cos t. Now we have a cos term, and as you know, if phi of t is cos of at plus b or sine of at plus b, we have to replace d square by minus a square. So here we have d cube term, so express that as d square into d. Now replace that d square by minus 1, we get minus d plus 8 operated on 65 cos t. Now it is a linear term, now minus d plus 8 is a linear term. I have taken 65 outside, I have taken minus outside here, so it is minus 65 into 1 by d minus 8 operated on cos t. We have a linear term in the denominator, and when we have cos t or sin t, we need d square term. So that is why you divide and multiply by d plus d. Then it is minus 65 d plus d, d minus d into d plus d is d square minus 8 square, minus 65 d plus d. Now you replace d square by minus 1, minus 1 minus 64 which is minus 65, and operate this d plus 8 on cos t. Derivative of cos t is minus sin t, and derivative, okay, and then 8 into cos t minus 65. Pi is 8 cos t minus sin t. Next, okay, this is pi, and solution is y equals to cf plus pi. So I have done few problems on Cauchy's differential equations today. In the next class I will solve some more problems with the different types, and then I will take up Legendre's differential equation. Thank you.